Welcome everyone to the Friday seminar. It's my pleasure today to introduce Dr. Marty Ralph, who's a researcher at Scripps, professor and researcher there at Scripps Institute of Oceanography. He's also the director for the Center of Western Weather and Water Extremes. This center, I was just on the phone with Marty, has really expanded over the years. It's quite impressive, up to 50 or 60 folks there working on a very important problem that he's going to talk to us about today regarding atmospheric rivers and impacts and so forth. Before we do that, a little background on Marty. He received his master's and PhD at UCLA. For many years, he was affiliated with NOAA. In fact, he was the chief of the water cycle branch at NOAA's Earth Systems Lab in Boulder for many years. And at that time, he won many awards, 3 silver and bronze medals with the Department of Commerce, 2 NOAA administrative awards. He's a fellow of the American Meteorological Society, and he's won a Climate Services Award there in the state of California. A lot of his work, as he'll be emphasizing today, is focused around water, especially the water cycle, which is very important on all time scales, as we all know. But his work covers everything from looking at the vapor transport of that water to the precipitation that falls out, the runoff, and everything in between. And so, and then needless to say, there's a lot of societal implications of that as well. And so I'm really thrilled that Marty accepted this invitation to talk a little bit about what he's been up to in that group there in the center there in California. So why don't you take it away, Marty?
Thank you, Brian. And thanks for the chance to join here and share some results with you from work we've been doing for some time, myself and a number of people I'll mention along the way. Also, I want to thank you for sending us Zhenhai Zhang and Minghua Zhang, and they've been very productive, and I'm hopeful for additional folks to join us here, I think, very soon. Alrighty, well, what I wanted to do is give you just a sort of an overview of recent developments in science, some of the impacts, and a little bit about policies, policy-related things. So the outline is going to be, from a background standpoint, from flood to FIRO. FIRO is forecast informed reservoir operations, and I'll dig into that a little bit. And then an overview of atmospheric river reconnaissance, which we've started and has become operational. I'll refer to that from OBS to gaps, from OBS gaps to impacts. And Minghua led a very nice paper that is now in press at BAMS. You can find it in early online release, and I'll highlight some of the key elements of that. And then also we've been building community, so from people to policies. First thing I want to do as part of the background is I'm an observational person at my core, not really a modeler. And we had a field campaign I co-led with Kim Prather and Dan Can. Kim is a aerosol specialist, so the little white strip on the background image is an aerosol plume intersecting an AR. We had support from NOAA, Department of Energy, NSF, California Department of Water Resources, NASA, and ONR, and you can see the ship and 4 different aircraft and a bunch of ground-based equipment. This was a real breakthrough for atmospheric river science. One of the main things that I was striving for it to do was to measure the water vapor transport in ARs more robustly than had been done before. Prior to this study, there'd been about 4 to 6 aircraft transects across an AR where we could calculate the horizontal transport of water vapor. And the average was something on the order of the equivalent of 10 Mississippi rivers. That was the average of the 4 to 6 cases, but we knew that that might not be representative, so we sampled a lot more cases. And here's the paper that presents that in 2017 in Journal of Hydrometeorology. And this actually built on data not just from CalWater, but also from other earlier studies, the 4 to 6 I mentioned. And you can see the different aircraft we used. The bottom left figure shows the white lines are the transect baselines for each of the 21 cases that we composited. The color background is the frequency of occurrence of ARs, so it's sort of like an AR alley. And we had a total of over 300 dropsondes we used. We defined the AR edges using a 250 kilogram per meter per second integrated vapor transport. I'll use the terminology IVT for that. It's basically you take the horizontal wind and the water vapor at each altitude and calculate the flux at that altitude and then integrate that vertically, and that becomes integrated vapor transport, surface to 300 millibars. So we found that when we composited these, the average width was 850 kilometers, and that about 3/4 of the water vapor transport occurs below 3 kilometers above sea level, and very little, less than 1%, occurs above 8 kilometers. So that upper level jet, which is so important for dynamics, is really not a player in terms of direct transport of water vapor. And the average maximum IVT was about 800 kilograms per meter per second. So we ended up drawing a cross section. I drew this on my PowerPoint thing one day, and it shows 3,000 kilometer baseline, more or less, or not quite that big here, 3,000 kilometers. And the blue shows the upper level jet in meters per second and ice attacks. And the black bold line is the tropopause, and you can see the tropopause fold there in the polar front coming down to the surface. The green lines are the water vapor mixing ratio. Notice we've got 9 grams per kilogram, 5 grams per kilogram. I skipped showing the 1 gram per kilogram, but it's basically around 1 gram per kilogram up here. So about 10 times more water vapor down low. But also notice the low level jet, the blue contours here, the dashed one, about 25 meter per second on average. The max is often close to 30. So it's about half the intensity of the upper jet, but 10 times the water vapor. So the water vapor transport is focused down low. That's this peach-shaped feature, and that's the average width and depth and all shown there. I like to think of this as a dipole. Essentially, the upper level dynamics, the upper jet is so pronounced and profoundly important, but the water vapor is tucked down low here near the surface, just ahead of the cold front. And one of the key findings is that instead of 10 Mississippi rivers worth of water, it's 26. So those 4 to 6 cases were not representative. We had to do more samples. And there's another paper I haven't cited here, but Guan et al., a year or so later, we looked at thousands of cases using reanalysis, and we looked at these 21 cases specifically and found that these cases were representative of thousands of cases. So we believe this cross-section and the related numbers are really good averages for the mid-latitude Pacific Ocean. Those robust results ended up helping inform the creation of the definition for atmospheric river as a term and a concept. The glossary meteorology editor had been requested for a couple of years to come up with a definition, and she got a hold of me, and we formed up a team, and the BAMS article written there you can refer to on our process to develop the definition. Because the topic had a little bit of controversy around it, we did a very transparent, open process for developing the definition that included 2 town halls, one at AGU and one at AMS. We had over 200 participants combined. We had, I think, more than a dozen panelists total, and 5 contributing authors to the paper and the definition. Fundamentally, a couple things we decided was, with a lot of input and feedback and discussion, was that they're really tied to extratropical cyclones, the way we're defining it. So it sort of said, basically, the tropics, we're not thinking of that as atmospheric river country. And then the other thing we did is we recognized that, the ARs feed into the warm conveyor belt, and that the warm conveyor belt can actually, because of the rainout it produces, be the end of the AR, the downstream end. Mountains on the West Coast often serve that role as well. It's not uncommon for us not to have a warm conveyor belt in some of the cyclones that hit the West Coast, at least the southern part of the coast. And those 2 mechanisms can cause the end of the AR in a way. And then also we decided that we didn't want to put quantitative thresholds in or methods for defining an AR in any sort of algorithmic way. And there's a whole community of people working on that now. There are a number of AR detection algorithms that are going. So the figures from that 2017 JHM paper from the 21 cases are the foundational figures in the AR definition. So most people are aware that ARs cause floods, and I want to highlight that here for just a moment. This is a picture, by the way, in the background by John Nielsen Gammon, who sent it to me one day. It's from north of Sacramento, and you can see the flood going on there. And another example on the left. Well, an example of the forecast challenge for flooding is shown in this figure, which is from our BAMS article on AR Recon. And you see here about 5 days of stream flow data, and each line is from a different forecast initialization time from National Weather Service of the stream flow at a flood-prone location called Guerneville on the Russian River, just north of San Francisco. The horizontal red line is the flood stage. And basically what you see is a DROUGHT portrayal here of the flood forecast from well below flood stage to well above flood stage, and it landed just a bit above flood stage. Just before the flood happened, they were preparing to do evacuations of thousands of people. And then the intensity of the flood forecast dialed back a bit. They maintained readiness to evacuate, but in the end, the storm came in such that there were not very many people evacuated. But it shows the sensitivity to, it shows the range of uncertainty in flood forecasting as an example on the West Coast, a range of 14 feet over just a few days of lead time. And well, was that a representative case? So here's a synopsis of several 8 flood events during about a 10-year period that we looked at the DROUGHT on. And what you see here is, from the left side is day 5, the vertical axis, so 5 days lead time, stage change. So the uncertainty in the forecast average is 10 feet at 5 days lead time. This is for a flood stage of 30 feet, where plus or minus a couple feet around that really determines whether or not there's evacuations needed. And there was a case where it was 20 feet, off at day 5 or day minus 5. And you can see how those the uncertainty reduces as you get to 1 day lead time, where the average is more like a couple of feet. But at 2 days and 3 days lead time, where a lot of the action is in terms of evacuation preparations, it's on the order of 4 to 5 feet, with some cases up towards 8 and 10 feet. And this is in our BAMS article on AR Recon that's in print, I think now in the August issue. So where does some of that uncertainty come from? Sorry for the cough, I have an allergy, that's all it is. So on the left panel, and this is from a paper by Andrew Martin in Journal of Hydrometeorology 2019. Black lines are contours of sea level pressure, so isobars. The color fill is the integrated vapor transport. The little purple area here is the Russian River. And the X is a shortwave or a secondary cyclone, or we call it a mesoscale frontal wave. And what we see on the right is one of those DROUGHT portrayals. In this particular case, there was an 8 foot of uncertainty in 2 days heading into it. And the paper shows, I won't go through all the details here because I want to cover a lot more stuff, but it shows how the uncertainty in this secondary cyclone or frontal wave modulated the conditions at the Russian River, causing this forecast uncertainty. So these systems that develop the frontal waves, very tough to get right in the models, and better initial conditions can help, and that's part of the motivation for atmospheric river reconnaissance. I also wanted to just highlight that there's a nice study by Limgiri et al. In Journal of Hydrometeorology this year, and it looks at 3-day extreme rainfall. Back in 2012, Mike Dettinger and I developed a scale for that. We call it the RCAT scale, and basically the map here in the upper left shows the distribution of where RCAT 1, 2, 3, 4, and 5 occur nationally. And what you see is the Gulf Coast, the East Coast, and the West Coast are where we get these big, 3-day totals. RCAT 4, for example, is over 20 inches in 3 days of rainfall. And then we looked at the co-occurrence of these 3-day totals that are extreme, and whether or not there was an AR present, or whether or not there was a tropical storm or hurricane present. And those bar charts below, and I don't want to go into all the details on that, but you can see them if you want to take a look at the paper. Fundamentally, we found that about half of all the RCAT extreme precip events on the Atlantic, Gulf and Atlantic coasts were actually associated with AR conditions. And you can see about 2/3 of all the RCAT 3 or stronger events were AR related. So this was a bit of a breakthrough study to really look at the relationship between extreme precip and AR occurrence across other parts of the country than just the West Coast. There have been a few studies, very good studies, one in the Southeast by Ben Moore and others, Fiorini et al. In the Midwest, that have shown the importance of ARs in extreme precip and flooding in those cases. All right, well, floods are part of the story, but also they're beneficial. ARs are beneficial to water supply. And this is a huge issue in the West, where water is a limiting resource, unlike in much of the eastern half of the country. And I'm from Michigan originally, by the way, lived in Florida for years growing up. But in the West, Water shortage can be a real impact on the economy. And you can see, of course, the terrible fires that are happening partly as a result of a very dry year on the West Coast. Turns out that 85% of the variation in annual precipitation in Northern California is due to how the top 5% wettest days vary from year to year. Those top 5 wettest days are almost entirely atmospheric rivers. So what this tells us is that drought and flood occur in Northern California because of either the absence of ARs or too many ARs or too big. So it's sort of important for S2S, for example, a very popular topic, to recognize that S2S outlooks for, the one wet season in the West Coast is, basically the fall to, through winter. And, to get the annual total right requires basically knowing how ARs are going to be. So now I want to turn, based on the water supply side, to a program that we've developed. My center leads with the Army Corps of Engineers and a local water agency in Northern California called Forecast Informed Reservoir Operations. And our initial pilot study is based on Lake Mendocino. The map on the right is about 100 kilometers north-south, and you see the watershed there. And I want to highlight down here, it's not shown, but Guerneville near the southern end is one of the most flood-prone communities in all of California. And Lake Mendocino is critical to water supply for about 600,000 people. There are endangered salmon on this river. Agriculture, which is a code word for grapes, which is a code word for wine. Some of the best wine in the world is here. It's a multi-billion-dollar a year economy, and it really hinges on water supply. Interestingly, the dam was built by the Corps of Engineers about 60 years ago and is operated for flood control by the Corps and for water supply by the local water agency. And let me tell you how that works. Here we have what's called a rule curve. Horizontal axis is October 1st to September 30th, which is the water year. The vertical axis is the storage in Lake Mendocino. And on the left part of that, you see what's called the flood control pool. The gray line is the rule curve. And it says basically if the water in this time of year ends up above the gray line, that water should be released back to the gray line to allow for flood storage in case there's another storm coming. And then in the spring, when the flood risk goes away, it's possible to refill the reservoir for enhanced water supply. This is pretty typical of how things work in quite a few reservoirs in the West. They're multi-purpose. And let me show you one of the challenges that is associated with this. Well, first of all, I want to highlight that this system has been fed for a century by a water diversion from the Eel River into the Russian River for hydropower by Pacific Gas and Electric. And about 15 years ago, that arrangement changed. The relicensing of that by the federal government said you had to reduce by about 50% the diversions from the Eel River because the salmon were having trouble in the Eel River. So these bar charts, that change from the left bar to the right bar is about a 50% reduction in the inflows into Lake Mendocino. Now the dam was designed presuming those inflows would be there forever. So it represented a big shift and loss of water for the reservoir. And this is one of the things that can happen. So here's one of these, water year summaries right here. This is about a year in the horizontal axis. There's the storage. The gold line now is the rule curve. The green line is the accumulated precipitation. And notice the, sort of the big jumps that occur here. And the blue line is the actual storage. Notice that it got down pretty low, and then there was a good storm that hit, and then another good set of storms. And those storms happened in March. And that's why we call it a miracle March, because the water was looking pretty bleak until right about here where we got hit by some good ARs. And that restored the water supply that then was used in the summer. And then we get into late November and we get the first big storm. And it's a whopper, which brought the water back into the conservation pool, or the supply side was refilled and it encroached into the flood pool. And then just a few days later, oh my gosh, it was another one. Now at this stage, the operators are supposed to release that water to get back down to the gold curve for safety in case there's another storm coming. And notice if you just extrapolate visually, another one of these piles on top, you're above the spillway of the dam. And now the river would be flowing with no control from the dam. And that's what water managers, flood control operators want to avoid at all costs. So they release the water just like they're supposed to, right down to that gold curve. And then what happened was very little rain fell the rest of the winter. That was around, the end of December is when they released that water, and that's the storms just shut off. And then that led us into a very bad situation in the summer. It turned out to be the driest 13-month period on record in this watershed. And the water levels down here were extremely low. It caused restrictions on water usage. It caused problems for the salmon and became a very politically serious issue. And people outside meteorology and water management looked at this water right here and said, why did you release that? Well, they really needed to, because they didn't have another option. The rules for this dam and for most dams in the West do not allow for use of forecasts, because the forecasts, when the dams were built, the forecasts were so lousy. The only thing that was allowed was to use rain gauge, stream gauge, snowpack, and water level in the dam. It had to be water on the ground. So our project, FIRO, is intended to test the idea that forecasts have improved enough that we could actually, allow for operators to consider keeping some of that water. And here's what we ended up proposing: is about 10,000 acre feet of additional water, which is enough for about 20,000 homes for a year. And if basically you had this water, this is a schematic of the past graph, and stopped releasing it here and kept it, if there was no AR predicted, and remember, ARs are the only source of flooding in this river. So it really boils the weather forecast down to an AR forecast. And if there's no AR in the forecast, then keep the water for another day, then look at the forecast the next day. And if there's no big storms that come, that water would then be available into the summer. Well, how do we figure out whether that's viable or not? We had to look at how long it takes to release that hypothetical 10,000 acre feet of water. It would take 2 days to release it from the dam, and then about 1 to 3 days for it to flow downstream. So that leads to a forecast lead time requirement of 3 to 5 days to predict landfalling atmospheric rivers. That begs the question about, it's basically a precipitation forecast skill problem. And I want to highlight a paper from a few years ago, Sukovich et al., Weather and Forecasting, 2014, where we looked at extreme precip forecast skill for 1 day lead time and top 1% and top 0.1% heaviest daily precip. And these are the WPC forecast skill assessments nationally on a 32-kilometer grid for a decade. And what we found was on the right here, we see, and we did it for the different RFC regions, River Forecast Center regions, which are mapped on the left. And I want to highlight these performance statistics. So probability of detection. The green bars are the Western US, and notice the high values there, good probability of detection. Northeast, interestingly, has the second best probability of detection, but much of the rest of the country in the cool season is much below that. And in the warm season, this right-hand column is warm season, the scores are much lower because convection, of course, is more important. We see similarly, false alarm rate is low in the West and in the Northeast, and critical success index is best in the West and in the Northeast. So we built this program on in a region where we have the best baseline forecast skill possible, and we know the storm type ARs. Let's look a little bit more at how we predict ARs nowadays. So here's a tool we've developed, and I have to credit Jay Cordera at Plymouth State University as being a major innovator on this. And what we see, there's a nice paper in 2017 in BAMS on this. We see on the left-hand panel here from 0 to 16 days out, and the vertical axis is the latitude, and each point here corresponds to a place on the coast. And take, for example, this 40 degrees north location, go over to the left, and we then can look at the GFS ensemble, 21 members, and we can see in this diagram the odds of at least minimal AR conditions, over 250 units of flux of IVT being exceeded in the forecast. And by the time we get out here to day 3, we see purple. That means that all of the ensemble members in GFS are saying at least 250 units of flux should hit this spot of the coast and would last the better part of a day, maybe even 2 days. And then you see there was a second AR in the forecast 7 to 10 days out, and a third AR, about 2 weeks out. We've come to be very skeptical of these type of signals that far out because they can go away. It could be a false alarm. But this is starting to be pretty, we've got some good skill in this time frame of 3 to 5 days now, and not good enough fully, but promising. And let me show you a winter-wide summary of that. Once again, from Jay Cordera, the vertical axis is the 16-day lead time now. Horizontal is the whole winter of this year. And the location is 38 north, right here, the red dot. And basically, we have the same color scale for probability from guess. And what you see essentially is that Out to 3 days, we don't get surprised very often, although there are some examples, like in here, there are a couple where 2 days or so. And then, we even see cases where out to 10 days, there's an early signal. So this is a really compact assessment of an entire year of skill from guests. All right, well, let's take a look at the development of AR Recon as a program and to help improve forecasts on the West Coast of ARs. You see myself as PI, Vijay Tallapragada, the director of GFS at NCEP, as co-PI, and JDoyle from NRL as a key person. We've developed a performance metric. This is from a paper by Wick et al. A few years ago. And we basically look at the predicted position of landfall in the left diagram here, and the actual, and that yellow arrow is the error. We did this for 3 winters. We calculated this out to 10 days lead time, the RMS landfall position error, using several of the leading global weather prediction models. And as an example, we see on the order of 300 or 400 kilometers uncertainty at 3 days lead time. Remember, an individual watershed is smaller than that. So what this says is often we see the AR coming a few days out, but we don't know exactly where it's going to hit. Well, how do we improve that forecast? Well, interestingly, right about the time we developed this analysis of forecast skill and the idea for AR Recon, a paper came out by JDoyle, Carolyn Reynolds, and others that used a moist adjoint method to show the sensitive region for initial condition uncertainty for a European storm. I called Jim the day I saw that and said, could you run it for the West Coast? Gave him a case. He ran it for this. The gray is the AR in the background in water vapor. And we picked a domain here of for verification and chose precipitation as the variable, and then calculated for, in this case, it was a day or 2 lead time, where the greatest sensitivity was in the initial conditions. Notice how the color lines map onto the AR. There's a few wiggles up here, which are important. I'll come back to in a moment. But now we've done many of these cases, 60 of them, and found the same basic result. So now let me summarize an assessment of where observations are now. Oh, so just going back. So what this paper does, it clearly illustrates we need to get the observations right in the AR offshore. So now the question naturally is, well, how do the observing systems do currently in measuring that? There's satellite data, for example, buoy data and the like, not much else, but those things, there's quite a bit out there. How do they do in measuring the AR? And here we have, for a framework, the schematic from that 2017 paper. The AR is here, and we see a cross section from A to A prime, 3,000 kilometers long. We'll define the cold side, the warm side, and the AR sector. And now I want to sketch the cross section of that schematically. And we see once again the tropopause in black, the frontal zone here in gray, the upper level jets down to 1 contour here for schematic purposes. The AR for one is in 1 contour. You see the dipole thing. But the main thing I want to highlight here is the presence of overcast cloudiness is very typical in and above an AR. And remember, the AR is about 3 kilometers deep. We often get overcast. So some of the satellite products that have trouble when there's clouds are not going to work very well here. And for example, cloud tracked winds, motion vector winds at mid and lower troposphere are very limited in their coverage in ARs because there's often high clouds blocking it. So this paper by Minghua Zhang in Press at BAMS calculates the performance of that. And we did that by looking at several individual cases. And here's an example of an AR. And we looked at where the different obs are. Here's the radiosonde data. There's, I think, NexRad VAD winds. There's surface obs, including buoys offshore. Now you see some data showing up offshore. Here's satellite data, and the green dots are low altitude motion vector winds, and the orange lines here are radio occultation data from satellite. And there's a few other satellite data points, the yellow ones here. But notice we're starting to see, the white patch there over the AR. There's a little bit of light blue dots in here. These are the higher altitude motion vector winds. And here the red dots are the AR recon sampling with dropsondes from the aircraft. And what we found essentially is that in the AR object itself, something like 75% of all the measurements of water vapor and wind and temperature are from the dropsondes. Here's a 3D schematic showing the obs relative to the AR without the AR recon and with. Now, let me summarize that schematically, or one more thing I want to, so there you see basically there is a gap in traditional observations of the AR object itself, and yet that's the region of the atmosphere that we've discovered is in fact the most sensitive. Let me emphasize that latter point through the paper by Reynolds et al., NRL, published I think last year, and this shows 60 cases of the moist adjoint targeting or sensitivity analysis. Here's our verification area on the West Coast, the black box, and the blue arrows are the composite IVT vectors over 250. The color fill is the sensitivity averaged, and you see the red and the blue overlap, and the black lines are the ED growth rate. So that shows us where the baroclinic instability is strongest. All of these things coincide essentially to the AR. Notice there's some spread north and south. That's actually an artifact of our compositing method where we did not correct the position for each event to align them to some common geographic point. So we're seeing the average of events that are spread across a larger geographic area. And this result is true for kinetic energy as a verification variable, and for precip, and for water vapor as the perturbation variable, and for wind as the perturbation variable. So what we're seeing is that basically the moist adjoint method is pointing directly to the AR as the place to ensure we have the best initial conditions. And to summarize that schematically here, I just want to highlight that we have the high sensitivity region corresponding with exactly where the AR is and exactly where we have the blocking of sampling by satellites due to clouds. Now let's take a look, why do we have that sensitivity? Wonderful study by Ruben Demerjian and company looked at simulations and diagnostics of case and found the following. If we take a moisture perturbation offshore in the AR and add moisture, it's going to modulate the latent heating. The latent heating will induce a transverse circulation, and that will be represented by mesoscale vertical motions, which are basically dynamically driven, and that enhances precipitation. In addition, if you put the moisture in, you get PV generation from the latent heating, which amplifies the wind, and with the moisture that's already there, amplifies the moisture transport, which then increases orographically driven precip. So these mechanisms, I think this is in Journal of Atmospheric Science, it's not in press, I think it's in print now, shows the physical process that makes the linkage between this moist adjoint finding the sensitive region being the AR. So now we have basically the schematic for AR Recon in a vertical cross-section framework is showing the dropsondes are filling the primary data gap in the lower and mid-troposphere associated with the AR and above it. Now in plan view, what does that look like? Here's a map showing our schematic objectives or strategy. And we see the West Coast, and here's our teardrop AR. The black lines are 2 flight tracks from C-130 Hurricane Hunter aircraft. And they're dropping sondes as they cross the AR. And remember, a dropsonde is released by the aircraft and parachutes down, takes about 20 minutes, measures temperature, pressure, wind, moisture very accurately at high vertical resolution, radios back to the aircraft, and then the aircraft radios it to the ground, and it's assimilated into the operational models. Now, we decided to do the same thing also with a third aircraft for this shortwave in Alaska. If you remember that sensitive plot from Doyle et al. Had little squiggly red and blue lines a little bit north of the AR. That's because there's some sensitivity out there with the shortwave. And I've brought this in personally because I think dynamically this is an important thing, because uncertainty in the shortwave and uncertainty in the AR can combine when both are present to create, I think, some of the biggest forecast errors. So we're trying to sample both of these features, the AR with 2 aircraft and the shortwave with 1. Well, that's nice. You can draw a schematic. Anybody could draw a schematic, but could we actually get airplanes out there in those places? And here's an actual mission with 3 aircraft flying over the AR in color, and the triangles or dots are the dropsonde locations. And you can see the G4 that came out from NOAA to the north sampled, this basically the shortwave to the north. There's the low pressure to the north. And then the C-130s from the Air Force sampled the AR itself. I should mention that this is now something we've done a number of times, and we've been ramping up on this. And as of a year and a half ago, the National Winter Season Operations Plan, organized by the Office of the Federal Coordinator for Meteorology, directs the nation's aircraft reconnaissance teams to, in NOAA and Air Force, do atmospheric river recon each winter. And we're leading it at our center. I'm the PI on it, and partnered with VJ Tallapragada at NCEP, and we've developed what we call a research and operations partnership to plan these missions, execute them, evaluate the results, refine the strategies, so on and so forth. Part of our ability to do that is based on having formed a steering committee, ad hoc, grassroots based, on modeling and data assimilation. And I won't go through all the details here. I just want to highlight our steering committee. I co-chair it with VJ, but we have Jim Doyle and Carolyn Reynolds from NRL, Adrian Subramanian from, he's now at UC Boulder, Chris Davis from NCAR, Florian Poppenberger, the director of forecasting at ECMWF, and Luca De La Monaca, data simulation specialist at my center. And I won't go through all the details here, but just know that we have a detailed plan, work plan, and each of these centers is now working together in coordination to evaluate the impacts of these SONs, and we're finding promising results. Here's a couple highlights of those results. The first is from NCEP in GFS with Vijay Tallapragada as the lead. And I'll just give you a little sample here. This is looking at the Pacific North American region 5-day lead forecast skill. And the summary of these, and there's, U and V winds at 500 millibars, 500 millibar height, and temperature at 500. About a 6 to 10% improvement can be attributed to AR Dropsonde data simulation. And as a bonus, we get about a 17% improvement in the wind analysis errors in the PNA region itself. So this is a hardcore NCEP, data denial study with our operational national model, the GFS, showing the impact across the northern Pacific North American region. Now, in addition, the Navy has done a study, and this is from Stone et al., 2019 monthly weather review. And what it shows is an analysis from a whole winter. And I'm just highlighting the concept here. This is the domain that we sampled with the AR Recon, the 3 aircraft. And this is, just it's sort of a reflection over the continent for scale. And you can see it's about a third of the, CONUS, but a much smaller fraction of the North American continent. Now, it turns out that the study Stone led compared the impact of these dropsondes with the impact of the North American radiosonde network, and found that essentially these dropsondes have even more impact than all of the North American radiosonde network in a key Northern Hemispheric skill score. So what this says is basically we're going to where the storms and the sensitivity are that impacts the forecast in the hemisphere. The radiosonde network is by definition geographically fixed in its location, and storms and sensitive areas go through that network, but some sampling isn't going to be as impactful as others depending on the forecast desired. So anyhow, we're seeing those results from the Navy. There's a whole set of papers that are published now. I'll direct you to these that are related to this, including a couple led by ECMWF, and there's one or two coming out of NCAR very soon. So we have a broad set of investigators looking at this and finding similar results in terms of impact. All right, let me see how I'm doing on time. Let me just wrap up with a few minutes on people to policies. So in 2016, after starting my center at Scripps in 2013, initiated the first International Atmospheric Rivers Conference. We had about 100 people attend, 75 presenters. It was well received and served a good purpose, and we repeated it in 2018 with about 125 attendees and 100 presenters. Then we did an AR summer colloquium where we brought about 30 grad students and 20 instructors together for 2 weeks and did a deep dive on ARs and their impacts. And then in 2020, our next IARC meeting, as we call it, was planned for Chile, but COVID shut us down in terms of in person, but we decided to hold it virtually anyways. And we held it just about 2 weeks ago. And we had something on the order of 120 presenters and about 400 attendees. We opened up the forum facility at Scripps that we usually use, holds up to 200 people. So the fact we went virtual allowed us to open the invitation to others. We did it with no registration fee. I sponsored it along with Renee from Garreau from University of Chile in Santiago. And you can see a map here for our summer colloquium of where people were from and where their studies were focused. And I want to highlight that there's been significant growth in the publications that refer to atmospheric rivers. Here's going back the first 10 years or so were a few publications. The topic actually more or less died. And then I wrote a paper in 2004, and you can see the growth in the topic here in terms of the usage and reference to it in formal peer-reviewed publications. Now the IARC meeting, the virtual meeting, just a couple weeks ago, we had a fairly complicated, agenda structure, and it went 4 hours each day for 5 days, and we had 120 speakers. And here's the survey at the end of whether the symposium was too short, too long, or just right. 80+% felt it was just right. 12% thought it was too short. So we, I think, found a format we can use to help build this global community working on the atmospheric river problem now. I want to highlight also a scale that we've developed. There's a paper in BAMS from 2019, myself and a number of co-authors, including some from Weather Service, from Climate, from TV meteorologist Larry Schick, and experienced forecasters. And the basic idea of the scale is that we have discovered ARs are important to both water supply and flooding, but the weaker ARs we've known all along are not really flood makers unless the ground is already saturated and all. So the public was interested in, well, can you help clarify which ones are going to be, hazardous and which ones aren't? So we developed this scale, and how it works is as simple as possible. You pick a single location and you look at the time series of IVT. And at the bottom here, I'm showing you a time series, and you got the vertical axis is IVT. And here the black line is the 250 unit threshold for IVT to define an AR. The blue line shows it crosses that at this point, and then it ramps up to its max IVT, and we call that the AR intensity. Then it drops down below the AR threshold, and that gives us the AR duration. And that allows us to then calculate the ranking on our AR scale. And we use this rubric on the left, where if the AR duration is 24 to 48 hours, then the ranking of the AR is based on the max IVT, or the intensity. And we define the intensity based on, or we have these terms: weak, moderate, strong, extreme, and exceptional. And that's based on the intensity alone. But if the duration is shorter than 24 hours, and otherwise we'd have an AR2, we demote it to AR1. If, however, it lasts longer than 48 hours, we promote it to AR3. And this is based on a study in 2013 I did that showed how AR time integrated vapor transport explains 75% of the variance in storm total rainfall. So we knew the duration and intensity combined are the key parameters. And here's an example of what one looks like in plan view. The AR scale is colorized there. The red is the 5. And this was the storm that hit Oroville a couple of years ago and created all the problems with the spillway and evacuations of almost 200,000 people. The black dots here show how the forecast changed 2 days ahead. Alrighty, so we have this scale now, and we applied it to look at flood damages. And the first step in that was, this is by a paper by Corringham et al. In Science Advances 2019. We looked at the Western US, 40 years of FEMA flood claim data. Remember, every flood claim has a location and a date and an amount. And because we have a catalog of ARs, we could actually then compare it with ARs. And this finding shows that in the Northwest coast, 99% in some cases of all the flood damages over 40 years were from AR storms. Averaged across the whole West, 84% of all flood damages in the West were associated with ARs. Well, we took the analysis a step further and asked the question, well, how do those damages relate to the AR scale? And here's the result. What we see is for the different AR rankings, we see a nearly logarithmic increase in damages. The colors are the 25 to 75% range. The black line is the median. And what we see is that AR 1s and 2s don't have much damage, well under 1 million median. But AR 3s are starting to get up into the millions. AR 4s are about 10 times that, and AR 5s are about 10 times that, up into the hundreds of millions. Now, there are cases, for example, where an AR 3 came in right on the heels of an AR 5 and created massive damage. And there are cases where even an AR 5 comes in, but the soil's bone dry and there's nothing to damage, and you get minimal damages. So antecedent conditions are the second most important thing, and is part of what we believe the human in the loop is important to convey in terms of public preparedness and situational awareness. And we're working with the broadcast meteorology community to hone our messaging in that regard. So mostly beneficial for AR 1 and 2, mostly hazardous for ARs 4 and 5. That's just a repeat accidentally. All right, now I want to just wrap up with a couple key slides on, here's our FIRO effort. I want to highlight that we started this study 5 years ago with an intent for it to be a paper study because the Corps of Engineers is very reluctant to change their operation of a dam. But our early results were so promising that the Corps actually asked us to submit a request for them to temporarily change operation of the dam to try out our method. And here we have the result from this last winter. In the third driest year on record in that watershed, normal operations would have been the brown curve. FIRO operations are the black curve. They were actually operated this way. This extra 11,000 acre feet exists in the reservoir and has helped get through the seriously dry summer that's been, the seriously dry period of year. Those results, the flood damages and the impact on water supply, have brought this work to the attention of our legislative leaders. And this is a picture from the House Committee on Transportation and Infrastructure. Grace Napolitano is the chair. And in her opening remarks, she highlighted FIRO and atmospheric rivers. And then I had a chance to share a few details in the meeting about how it works. And after the meeting, she was very interested and personally approached to ask that we do more of it. Now, this committee is actually the committee that lays out the national strategy for water management and flood control through what's called the Water Resources Development Act, WRDA. So they were inviting this briefing as input to the next update to WRDA. In addition, the broadcast media is starting to recognize that some storms are more important than others, and they're broadcasting this now in their products live. In addition, on the climate side, ARs have become recognized on this to be in the same category as winter storms, severe convective storms, and tropical cyclones in terms of warranting investigation of climate change impacts on them. This is from the 4th National Climate Assessment. In addition, Springer just published a book released in August on atmospheric rivers, the first such book. I'm the chief editor. We have co-editors Mike Dettinger from USGS, Jonathan Rutz from Weather Service, Dwayne Walliser from NASA, and 34 contributing authors from around the world. Finally, I'll just close with our center at Scripps was formed in 2013-14 when I went there to start a center. And then 5 years in, we decided to update the strategic plan. And here we have the strategic priority areas: our FIRO, subseasonal to seasonal prediction, atmospheric rivers research and applications, modeling for the Western US, climate variability and change, and then emerging technologies. And I want to acknowledge the team effort that it takes to do all the work that was presented in the seminar here. This is for the most part the members of our team. There are a few visitors. You can see, for example, Lance Bozart and Chris Davis in front. And this was from a year ago when we could still meet in person. And then here we have the contact information. So thank you very much.
Great. Thank you so much, Marty, for the nice talk here on ARs. So I'm going to open it up for questions. If you can just raise your hand, then we can take them. And so we'll start with Joseph.
And thanks, it was a really interesting talk. I was just wondering about the political side of it, as to whether you've heard any pushback from people who have representing districts which are particularly flood prone.
It's been just the opposite of pushback. There's interest. One of the challenges in Western flood management and Western prediction is that there's been a lot of attention on Eastern US and Central US weather types and not nearly as much on the West. And now we have a framework in terms of the science of ARs and the tools we've developed to predict them and understanding of uncertainty in the forecast and how that maps onto flooding, that they're recognizing the importance of pursuing this further.
Right, I guess what I mean is just specifically about leaving more water in the reservoir, which like makes sense. But I guess if you were in somewhere that was really, really flood prone, then maybe you'd have that as a higher concern than the drought.
I misunderstood your question, sorry. So yeah, that's the reason we took a very measured and scientifically rigorous and engineering-based approach over 5 years to assess the viability objectively of FIRO on Lake Mendocino. That is literally the most flood-prone place in the Western US. And we work with the water managers and the leaders in the community who run the reservoir and we've got results that are just rock solid.
Thanks.
Okay. Thank you, Joseph. Jaime, you have your camera up. Do you have a question?
Yes. Hi, Marty. Thank you very much for the nice seminar. I actually have two questions. So you showed the category 1 to 5 AR, the AR category. What is the focus skill sensitivity by the categories? Is the category 5 more predictable, or is there any study out that shows the focus skill?
That's a good question. Nothing comes to mind that we've done yet. So that's some work remains to be done. And I should mention that although my paper uses the term category, we've come to recognize from feedback from the public that what they get confused, they automatically start thinking of hurricane. So we have chosen to remove the terminology category from the scale, the usage of the scale, and we call it AR ranking.
Oh, okay. Another question is, you mentioned briefly about the subseasonal to seasonal timescale. Can you explain a little bit more about your what's the center's ongoing activity on S2S forecast?
We have several experimental S2S products that are under development and testing, and some are AR related, some are not. They range everywhere from 2 to 4 weeks out to 5 to 6 weeks out to months ahead to seasons. And we're exploring both the pushing forward using weather prediction capabilities, basically, that are explicitly resolving ARs to see if there's some skill at weeks 3 and 4. Nice paper by DeFlorio et al. Documents that, and there is some, in some circumstances, some skill out at weeks 3 and 4, mostly week 3, 4 is a stretch. But there are also circumstances when, for example, a strong MJO is present and the QBO is in the right phase. Some work by Libby Barnes and Muntank et al. Have looked at this, and we've adopted some of that shows that weeks 5 and 6, under the right conditions of QBO and MJO, there is some skill in the AR probabilities for the West Coast.
So
and then we go farther out with other tools.
So that's mainly empirical focus, right? The MJO QBO combination. So you're.
I didn't catch the word there. What type of forecast?
It's the empirical forecast.
Yeah,
Okay.
Not dynamical, yeah.
But your center will have the both dynamical and empirical forecast. Is that the plan?
That is, yes. We're doing both. What we have is a process of I have an advisory group, and we review progress in S2S prediction in our group and tools that we're developing. And once we have a publication that documents rigorously documents the method with its uncertainty quantification, we will then roll it out as a real-time product that is available online.
Okay, thank you. And there was one paper about the machine learning for AI prediction recently.
Chapman et al.
Is that also planned?
Yes, we're using that as well. That's by Will Chapman, one of my PhD students who's nearing completion. And it shows a significant jump in skill for IVT out to 7 days, based on machine learning approach to correct the IVT fields.
Mm-hmm. Thank you very much.
You're welcome.
Okay, Edmund has a question. Edmund Chang.
Yeah, Marty, this is Edmund Chang. Nice talk. Yes, yeah, Inba was my student previously, so you mentioned her work, so that's nice that she's doing well at your center.
Yeah,
so I have
well.
a question. So you talked several times about the winter reconnaissance, the AR reconnaissance program, yes. And I haven't read the paper, but you did mention that there are several projects going on to assess the Dropsonde, the effect of the Dropsonde. So have you shown that including the Dropsonde actually improved the AR forecast itself? Because you showed some results that suggest improving the sort of large scale UV and thing. So have you assess the AR prediction itself?
There are some preliminary results in that direction, yes. Edmund, it's been one of the deeper frustrations of mine that it's really hard to introduce new performance skill metrics into the modeling community. And, you know, it's just taking longer to get there.
So actually, before, I think Kevin may have a question, but just to build on that, because I was curious about the reconnaissance and your time scale, which is sort of 3 to 5 days to really have a big, you know, impact on what decisions need to be made. And when you think about those time scales, you also sometimes have to worry about the Western Pacific and what's going on way upstream. And I'm just wondering how you deal with that, if there's, you know, a typhoon in the West Pacific and how that may affect downstream development.
Yeah, good question, Brian. And I do want to make sure I correct maybe a misstatement I made. There is challenge at day 1 and 2 as well. So for example, the terrible Montecito debris flow that took 20 plus lives a couple of years ago, right after that was another AR predicted heavy rain, but it was predicted to hit that area again. And they evacuated 10,000 plus people who were terrified. And it turned out the AR hit Big Sur. So just at 24 hours lead time, in that case, it was about a 200-kilometer error in the position of landfall. So we have cases where, you know, with the shorter lead times, we need to work on improving it. And there was one of those up in the Northwest last winter. So yeah, the West Pacific is really ripe. We should be thinking about that. And in fact, we're thinking about the Atlantic right now as well.
Yeah, Kevin, did you have a question?
Yeah, hi, Marty.
Hi, Kevin.
I have maybe more of a big picture philosophical question. You know, you did a good job in your seminar kind of providing us almost a little bit of, you know, kind of a history of how you've gotten to where you've gotten in terms of you know, the center, as well as kind of understanding and categorizing and forecasting and talking about the impact and applications of atmospheric rivers. And some of your motivation about that was the fact that, you know, that was maybe underappreciated in terms of Western extreme events compared to more historical things like, you know, severe storms and hurricanes, which have, I guess, a pretty large, complex, you know, government, non-governmental program in which they forecast these things. They come up with these categorizations, and it's probably orders of magnitude more money in the grand scheme of things. Yeah. And I'm curious if you know, the approach that you guys have built to do basically something fairly quick, right, in under a decade, compared to other places that have been around for 50 years. I'm curious if there's been discussions within NOAA or if you've had discussions about how, you know, if there's ways within the HRD process or the Severe Local Storm Center process in which they can learn from some of the ways in which you guys have engaged with stakeholders in kind of a local level to maybe improve some of their products. Because I think, you know, your last comment there about how it's really hard to get new metrics into the modeling community, I think in even more established communities like the, you know, like the Hurricane Center, it's probably even harder to make those advances and get new metrics in. And so I'm curious, it's kind of an open-ended question, but I'm curious about some of your
very good question, Kevin, and it's good to see you, by the way. And I want to mention just one more bit of my resume that didn't come up is I spent several years as a program manager in NOAA leading the U.S. Weather Research Program, and turned it towards investing and seeding test beds, you know, weather-related test beds. And that, you know, was taken off. There's a nice paper in BAMS that summarizes half a dozen or so of those test beds that got rolling. But it was still hard to do the innovation and to get it through into operations. So I also ran a program called Science, Technology, and Infusion, which was about a $100 million a year program for planning, where we objectively identified gaps in forecast skill, science directions to improve on that, including hurricane intensity, severe weather, precipitation, even tsunamis were in my program initially, and better OBS, better IT systems, things AWIPS 2, dual pole upgrades were part of my program as well. So I've been through the ringer on how to do innovation and transition it into operations. And there's a lot of obstacles there. It works, and there's some real successes, and we have good forecasts today because it does work to a substantial degree. What I found though was in the opportunity of going to the university and operating from a university setting, doing experimental work where the products are, we're doing real-time stuff because that's really hard to do and to get it right. We're measuring our performance, we're developing metrics and bringing the science to bear, the observations, the modeling, and doing it with a lot of freedom to do innovative stuff and try out, how those new improvements in the science or the observations or the modeling in some fashion or the post-processing can actually yield a better forecast in the end. And we're doing that with the door wide open to collaborate with Weather Service, including the WFOs are apparently using our products all the time. The river forecast centers as well, primarily in the West. And we're working closely with NCEP, like the relationship with VJ Tallapragada, the director of GFS. So we're just working it from a totally different approach, from a university setting where we can be very innovative and we can be funded by NSF, by NASA, by a variety of agencies. When inside NOAA, it's much harder to work out that funding. I don't know if that answers your question at all.
No, yeah. I mean, I think it was an open-ended and challenging question. So I think maybe I'll just kind of follow up real quickly and from the perspective that there's this push within the OSTP as well as kind of broader in the community to talk about practical predictability and Earth system predictability from the sense of kind of a holistic view from the kind of the whole kind of weather enterprise, weather climate enterprise at that point. I'm just, I think Dwayne, for example, is part of that process, at least at the National Academies, and has really pushed this systems approach, right? And I think that's partially what you were kind of outlining in the approach that you guys have done at the center, which is a little bit more of a systems approach and a kind of being open to innovation, allowing people to connect in different parts and clamp in when they need to, but also kind of do their own thing. I think that's something that I hope probably works its way out in whatever comes out of this process that the National Academy as well as NSF and a few different agencies are doing separately, because it seems to be maybe a way to keep things more fluid in the future, as opposed to kind of once they get rigid into government labs, they often, things start to move at a snail's pace sometimes.
Yeah, and it's natural that it moves slower. The bigger the organization gets, it has more responsibilities, more things it has to keep going. And the budgets, frankly, for the federal agencies have been really hamstrung by politics. So, we have a lot more options externally. I do want to add that another part of what I saw, as a program manager, running grants programs where there's, proposals submitted, reviews and decisions and all that, plus the planning program of developing new ideas. I've come to believe, and maybe this is a little bit off, not, the typical view, is that the typical request for proposals nowadays in our field receives something like 5 to 10 submissions for every proposal selected. And the process forces us to compete with one another aggressively, right? To be able to, get the funding needed to do the work that is so important to do. That compete with one another thing I view as somewhat of a corrosive thing in our community, and it's a waste of energy in some cases. So I've moved towards these partnership approaches where it's much more a directed research philosophy, where the teams are chosen, there's some competitiveness involved, but it's largely a collegial environment where we're working together to achieve a common goal. And in building the center up, my approach, when I started it, I was hoping if there was enough funding, I could basically reserve about a quarter of the funding to send out as subawards to colleagues who would want to work with us to bring their knowledge, so I don't have to duplicate their capability. They have years of experience that could then feed into our center's success. And if our center succeeds and the subaward's been effective, then there'll be more of that. So it becomes a symbiotic relationship rather than a competitive one.
Great. Thanks, Marty.
Sure.
Any other questions here?
So
Dalton, yes.
I have a question. Yeah. Oh, hi. So my question is that the path of the atmospheric river and of course the moisture flux is related to where the subtropical high is and how strong it is. So is that being looked at in your center in some way in the work you are doing?
We do have some results on the subtropical high. In fact, Zhenhai Zhang in my paper a year or two ago showed that for about 20% of ARs are not associated with an extratropical cyclone within 1,000 kilometers, but they are associated with an anticyclone to the southeast.
I see.
So, and the strongest ARs have both a good extratropical cyclone on one side and a good anticyclone on the other side. It's sort of intuitive if you think about it, but we put some numbers to that. So yeah, right on.
So, but does that this insight play a role in making the forecast you are making?
When we look at the moist adjoint and other methods we're using, the anticyclone has not been showing up as a significant player in terms of initial condition uncertainty.
I see.
Not to say the tools are fully capturing that, and maybe there's something there, and we should look at it, but it's not at the top of the sort of indicators right now.
Okay, well, thank you so much.
You're welcome.
So Marty, I don't see any others, but the last question I have, kind of building on Kevin's, because we all know NOAA, the government's kind of been trained, especially on the modeling side, and there's a lot of duplication of effort. And I agree with you on the proposal process, that surrounds all that. One new area though, which I keep wondering if NOAA would be more flexible or if there could be more community involvement, is on the social science side. And how to communicate uncertainties at different timescales and risk. This is a new area for NOAA, and they only have a handful of people working on it. And it just seems like maybe that's an area that's ripe for real community collaboration in some sense. And I'm just wondering, well, first, I mean, you showed some examples how you're moving in that direction, but how do you feel about this area of growth?
I think it's a vital area, Brian. I think you're right on. And the things I described about our tool, about scale, about rolling it out to the media, we're working with them directly to try to figure out how to test things out. Working with the weather forecasters as well, and the Weather Service forecasters as well. And I think it's a really key area to be investing in. And we're doing the innovation. But when the time comes and the value's been demonstrated, NOAA will have a choice to make about whether to incorporate it internal, use of the scale in particular. They're sort of watching how we're doing it, and we'll see what happens. But in the meantime, we really can't afford to wait because there's so much hinging on these storms, and we have methods now that have been developed that are proving valuable. So yeah, I think the universities and innovation and private sector is doing a lot of innovation, I think, and NOAA is able to absorb some of that, and they have a certain capacity and some strength, and then some limitations as well.
Great. Well, thank you so much, Marty. Give you a big round of applause. At least you can hear me.
Thanks.
So on behalf of everyone here, thank you so much for your time. I know it's 3 hours earlier there on the West Coast.
That's all right.
So I really appreciate your time here this morning.
It's a pleasure.
Very insightful seminar. Hopefully everyone learned a lot here. And thank you again, Marty, and everyone. Please have a great day, a great weekend. So,
likewise.
Yeah.
Thank you. Bye-bye.
Thank you so much, Marty.
Bye.
And thank you, everyone.